Hello everyone, and welcome to our video on volumes by cylindrical shells. So the previous techniques that we discussed for finding volumes are not always effective. For example, if we try to find the volume of the solid found by rotating the region bounded by y equals x squared minus x cubed and y equals 0 about the y-axis, this would require solving y equals 2x squared minus x cubed in terms of y, at least to use the disk method. So why is that? Well, this is not exactly a graph of this function, but remember, if we're taking some shape like this, and we are rotating it about the y-axis, then if this is a disk, the thickness of the disk is going to be measured by the y-axis, right? We're going to have dy is our thickness, which means we need to integrate with respect to y, and that's why we would need to rewrite this. But of course, we don't really have any good algebraic way to rewrite this 2x squared minus x cubed in terms of y. So instead, we're going to come up with another approach to evaluating volumes of rotations, of solids formed by rotation, and that's the method of cylindrical shells. So in order to do that, first, we're going to look at, well, what is a cylindrical shell and what is the volume of a cylindrical shell? So we've got an image over here to the left, and that's a cylindrical shell. It's literally just a cylinder like a pipe that has some level of thickness to it and is empty in the middle, like a hollow pipe. So it has height h, an inner radius r1, so that's the radius from the center of the pipe to the inner edge, and outer radius r2, so that's from the center of the pipe to the outer edge of the pipe. And then we can label an average radius that we're going to call r. That's the radius out to the center of the pipe portion. So, key fact, if r is equal to r1 plus r2 over 2, in other words, the average between r1 and r2, and delta r, the thickness of the pipe, is r2 minus r1, then the cylindrical shell has volume that can be written in the form 2 pi r h delta r. Okay, let's go ahead and prove that. So, proof. Let V1 be the volume of the inner cylinder and V2 be the volume of the outer cylinder. In other words, V2 is the whole volume of this whole construct, and V1 is the volume of the empty space in the middle. And so the actual volume of the shell is V2 minus V1. And so that's pi r squared, r2 squared h minus pi r1 squared h. That's just the regular volume of a cylinder formula. So we've got the volume of the outer cylinder minus the volume of the inner cylinder. And of course, we can factor out pi h from each of those terms, which leaves us with r2 squared minus r1 squared. And that's difference of squares, so we can factor that to pi h times r2 plus r1 times r2 minus r1. And of course, r2 minus r1 is delta r. And if r is r1 plus r2 over 2, then r2 plus r1 is twice r. So altogether, that gives us 2 pi r h delta r. But if you think about that, that's the same thing as saying the volume of the cylindrical shell is the circumference, 2 pi r, times the height times the thickness of the shell. Circumference times height times thickness. And that's going to be an expression that you really want to memorize, because that's going to be the key to finding volumes using cylindrical shells. So how do we use this idea to find the volume of a more general solid? So take a look at the two images. We're going to consider this graph here rotated about the y-axis. So you're going to get a three-dimensional figure that looks something like this. Hold on, that's not quite right. Let me fix that. Okay, it's not perfect, but you rotate this around and you get this three-dimensional figure. Looks kind of like that. I'm not a good artist. Forgive me. So, the idea though being, all right, we've got this three-dimensional solid that we want to approximate the volumes of. How can we do that? Well, we can do it by approximating it using stacked cylindrical shells. And that's what this image here on the right is. But just to make this image more clear, I'm going to pull up a full 3D graph of this thing so we can take a look at it. I couldn't get this one imported into the document directly, so we'll just look here. So here we've got this graph for y equals the square root of x plus 1. That's the green graph here. And then here I don't have a rotation graphed in here of this thing, but just imagine this is graphed and rotated, and you're trying to find the volume. And so you stack a cylinder amongst the rotation, the first rotation, the innermost rotation, and then you stack another cylinder outside of that, and another cylinder outside of that, and you add up the volume of the three cylinders, and that gives you an approximation for the volume generated by that region rotating that curve around the y-axis. Okay, so that's the idea of cylindrical shells. Okay, now how do we do it in practice? Now you should probably just erase whatever extra marks I put on here because they're, you know, I'm not a good artist. So let's move on. So since we can approximate the volume with the sum of the volumes of cylindrical shells, we can write that the volume is approximately the sum from 1 to n of 2 pi x sub I star times f of x sub I delta x. Again, this is circumference times height times thickness. So each of the expressions inside the sum is the volume of one shell. And we're adding n of those shells together. So, blah, 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 take the limit as the number of shells approaches infinity, and what do you get? You get an integral. So we've been through this a few times now. So, case 1, let S be the solid obtained by rotating the region bounded by y equals f of x equals a, and x equals b about the y-axis, where f is continuous, f is positive, and a is smaller than b, and also positive, or 0. Then the volume of S is the integral from a to b of 2 pi x f of x dx. In general, we think of this as the volume from a to b of the circumference times height times thickness. Okay, so we'll try to put that into application on that problem we discussed earlier. Find the volume of the solid obtained by rotating the region bounded by y equals 2x squared minus x cubed and y equals 0 about the y-axis. Okay, so first let's find some intersection points. So we set this function equal to 0, 2x squared minus x cubed, gives us x squared times 2 minus x is 0. So x is 0 or 2. And then the corresponding y values would be, let's say I plug in 0 for x, I get 0. And of course, the intersection point is y is 0 for both of them, so I actually don't even need to check the second one. So my intersection points are 0, 0, and 2, 0. And just to get a slightly more complete picture of the graph, we'll plot one point in between, say x equals 1. I get 2 minus 1 is 1. This is not an exact picture of the graph, but the region we're concerned with looks something like this. Now, we're trying to rotate this about the y-axis. So what I want to see for your cylindrical shells is I want to be able to identify what the radius is, right? Because what are we looking for? Circumference times height times thickness. Circumference is 2 pi r times the height times the thickness, which is d, whichever is appropriate for the problem. So I want to see you draw basically a rough shell. So we've got a top and bottom function. So pick a point on your graph, draw a straight line between your upper and lower bound here. And then take that line and rotate it about the axis of rotation. So our axis of rotation is the y-axis. So I imagine taking this line and just rotating it here. And that's my cylindrical shell. The key things being, we need to be able to figure out what the height of the shell is. So the height, that's pretty straightforward in this case. It's the distance from y equals 0 to the function, to the graph. So it's literally just the y value of the function. And the radius is the distance out from the y-axis to the point on the cylindrical shell. And that's just some x value, right? Because again, remember, we're stacking a bunch of cylindrical shells here together, like in that picture we looked at earlier. So let's look back at that. We're stacking a bunch of cylindrical shells, and each one has a corresponding x value that you're taking the height of the function at, right? So if we look at these, I took the height of the function at these points to build my cylindrical shell. And so for each cylindrical shell, there's a different x value. I just need the general expression here. So my radius is the distance from the y-axis to some x value, so my radius is just x. And the thickness of the shell is the thickness of the wall of the shell. So again, look, this is delta r here. So we're asking what axis does our delta r, does the thickness of our shell get measured on? So like if we look at this picture, when we've rotated about the y-axis, the thickness of each of these shells lines up with the x-axis. So dx there. And now that we have that, we can set up our volume formula. So always keep in mind that your bounds for your integral, these formulas are all derived using the bounds of the original region you drew. So if I highlight the original region we drew, this is the only thing you look at when you're determining what your bounds are for your integral. And since we're integrating with respect to x, I use the bounds for x from 0 to 2. 2 pi r circumference times height times thickness. That's the key here. I really want you to try to burn that phrase into your mind. Circumference times height times thickness. That's it. Every one of these problems, you're just going to have to determine what's the circumference, what's the height, what's the thickness, and then integrate. Okay, so next I'm going to distribute this x across here and pull the 2 pi in front of the integral. That gives me 2x cubed minus x to the 4th inside the integral. This is 2 pi times 2x to the 4th over 4 minus x to the 5th over 5, evaluated from 0 to 2. That's 2 pi times 2 over 4 is 1/2, so 1/2 2 to the 4th minus 2 to the 5th over 5 minus, and when I plug in 0 for both terms, I get 0. Now 2 to the 4th over 2 is 2 cubed, which is 8, minus 2 to the 5th, that's 32 over 5. 8 is 40/5 minus 32/5. That's 8/5. So this is 2 pi times 8/5, which finally is 16 pi over 5. Okay, so that's it. And again, a lot of these integrals are going to be fairly simple to compute. The integrals really aren't bad at all. What is challenging is setting them up properly. So you've got to make sure you draw a good descriptive picture that shows your region, that shows what a sample cylindrical shell looks like, and that you can use to interpret what your radius and height and thickness are. Okay, let's look at another example. Find the volume of the solid obtained by rotating the region bounded by y equals x and y equals x to the fourth about the y-axis. So the first thing I'm going to do is find my intersection points. We've got y equals x and y equals x to the fourth, so I'll set x equal to x to the fourth. Subtract the x, I get x to the fourth minus x is 0, and factor. X cubed minus 1 times x is 0. So x is 0, or x cubed equals 1, but that also means x equals 1. And now I'll find my y values, and again I can plug into either function, because these are intersection points, these are where the functions are equal. So I'll plug into the simpler function, y equals x, so I get y equals 0 and y equals 1. Okay, so one of these is the straight line with slope 1, that's y equals x. And the other graph is the fourth power function, which looks a lot like x squared, just a little more extreme. Looks like this. So we've got our intersection points. And now we have to imagine rotating this graph about the y-axis. So I'm going to draw my mirror image region here. And let's do, I want to pick a distinct color here. How about yellow here? Okay, so we want to draw our cylinder. So you've got your top and bottom region. Here's your two regions, or your two curves, I should say. I want you to draw a straight line between them. You're fixing a single x value here, drawing that straight line between the two curves, and then rotating the whole line around the y-axis. And so in this case, the height is a little different because the height of our cylinder, if we try to, say, zoom in a little bit here, the height of our cylinder is the height between the two functions. So the height here is the top function, so y1 minus y2. It's the y values subtracted, but the top function is the straight line, y equals x, so I get x minus the bottom function, which is x to the fourth. Now the radius, again, is the distance out from the center of rotation, which is just the x value. And the thickness, again, is dx. Okay, so now we can set up our volume. And the volume is the circumference, 2 pi times the radius, times the height, x minus x to the fourth, times the thickness. And we're looking at our original region. And we're integrating with respect to x, so we look at the bounds of the original region with respect to x. That's 0 to 1 for our integral bounds. Okay, I'll distribute that x, and I get x squared minus x to the fifth. Pull that 2 pi out in front and take my antiderivative. I get x cubed over 3 minus x to the sixth over 6, evaluated from 0 to 1. That's 2 pi times 1/3 minus 1/6 minus 0. Again, in this case, we're plugging in 0, so both of those second terms are going to disappear. 1/3 minus 1/6 is 1/6. So that's 2 pi over 6, or pi thirds. Okay, that's it for that one. Let's move on to another example. Find the volume of the solid obtained by rotating the region bounded by y equals the square root of x equals 0, and y equals 2 about the x-axis. Okay, so let's go ahead and start drawing this. Now, we don't have two separate distinct functions, though you could say x equals 0 and y equals 0 are functions, but we're going to think of those more as vertical and horizontal lines. So we've got boundary from y equals 2. We've got a boundary for x equals 0. And then we've got the curve, the square root of x, which we know when x is 0, y is also 0. And how do we find when y is 2? So if y is 2, I get 2 is the square root of x, so x is 4. So this is the region that we're concerned with right here. And we're rotating this way this time. So we're rotating the opposite way. And that tells us that we're going to be integrating with respect to the opposite variable. So if I'm rotating here, imagine this is my axis of rotation. I have to draw a line parallel to this axis of rotation. I'm drawing a line parallel to that in my region that connects a top and bottom portion. And I'm rotating that around my axis of rotation. And now I have to determine my height and my thickness and my radius. Now it's a little tricky because this shell is sideways. So you have to keep in mind, you can basically turn your head 90 degrees to the right and look at the cylinder that way. And that's how you should be viewing this. So if I turn my head to the right, 90 degrees, I go, okay, then the thickness of my shell is being measured on the y-axis, dy. The height is this distance right here, which is the x value of the point on the green graph. And the green graph is the square root of x, right? So my height here is the x value. The height is the x value, which is y squared, so that should just be a y squared there for height. It's dy. This is 2 pi times y cubed dy. That's 2 pi times y to the 4th over 4, evaluated from 0 to 2. Pi over 2. So 2 pi over 4 is pi over 2, and y to the 4th becomes 2 to the 4th minus 0 to the 4th. That's pi over 2 times 16, which is 8 pi. Okay, that makes a lot more sense. Okay, let's dig into another example. Find the volume of the solid obtained by rotating the region bounded by y equals 4x minus x squared, y equals 3, about x equals 1. Okay, so first of all, we've got y equals 4x minus x squared. Let's find the vertex for that. So dy dx is 4 minus 2x. So this derivative is 0 if x is 2. And if x is 2, we plug in that 2, we get 8 minus 4, y is 4. So that's my vertex for my parabola. And we also want to find our intersection points for x minus x squared equals 3. Move the x squared across and the 4x. And factor, we get x minus 3 times x minus 1 equals 0. And so x is 3 and x is 1. And the intersection points for those are both y equals 3, because we can just use the simpler function. So those are the intersection points. And now let's go ahead and draw this thing. Okay, so the intersection points are 1, 3, and 3, 3. And the vertex is x2, y equals 4. So this is my parabola here. And we'll do that in green. And then y equals 3 is the lower bound of that. And it's rotated about x equals 1. So that makes this one a little bit trickier. So this is our axis of rotation here. So now, as always, I'm going to draw a line that's parallel to the axis of rotation inside my region. So this will be my line. And I take that and I rotate it around my axis of rotation. Now, the reason that that makes this tricky is because my radius now is not just x or y, because remember, radius is really the distance from the point on your cylinder to the axis of rotation. And so now that radius isn't just an x value, it's the distance from x, whatever that x is, to 1. So that's x minus 1. So this is the larger value, x is the larger value, minus 1. That gives me a positive radius here, x minus 1. Okay, so now we've got our radius, but we need our height. So our height is the vertical distance between these two things. So that's like y2 minus y1. And the top function is 4x minus x squared minus the bottom function, which is 3. And of course, I think it's pretty clear that the thickness of the cylinder is dx. So let's jump into the volume now. 2 pi times the radius, which is x minus 1, times the height, which is 4x minus x squared minus 3, times the thickness, which is dx. And as always, we look at our original region to determine our integration bounds. And so that's from 1 to 3 on the x-axis. So 1 to 3. And now the rest is some plug and chug. Now this one's a little more tedious because we got a bunch of algebra to do, but it's still not too challenging. So we distribute the x, and what do we get here? We get 4x squared minus x cubed minus 3x, and then we distribute the negative 1, and we get minus 4x plus x squared plus 3. Now we want to simplify this expression before we compute any actual integrals. Okay, so our highest power term is x cubed, and we just have the negative x cubed term. And then we've got 4x squared plus x squared. So that's plus 5x squared. Then we've got negative 3x minus 4x. That's negative 7x. And finally, we've got a plus 3. So now we integrate. That's 2 pi times negative x to the 4th over 4 plus 5x cubed over 3 minus 7x squared over 2 plus 3x evaluated from 1 to 3. Now we plug in. And then we got to do some simplification here. So 3 to the 4th, that's going to be 81. So negative 81 over 4. 3 cubed over 3 is 3 squared. That's 9 times 5. That's 45. Minus 9 times 7 is 63 over 2. Plus 9. And then we're going to distribute this negative. So we get a positive 1/4 minus 5/3 plus 7/2 minus 3. And then we'll try to clean that up a bit. 2 pi times. Okay, we've got negative 81/4 plus 1/4. That's negative 80 over 4, which is negative 20. So that's negative 20. And then let's do all of our whole numbers. 45 plus 9, that's 54. Minus 3, that's 51. Then we've got 63 halves, negative 63 halves plus 7 halves. So that's going to be 56, negative 56 halves. And then minus 5/3. Okay, so 56 over 2, that's going to be 28. So that's minus 28. Minus 28 minus 20, that's minus 48 plus 51, that's 3. So I've got 3 minus 5/3. All right, 3 is 9/3 minus 5/3, that's 4/3. So 2 pi 4/3, and that's 8 pi/3. And I would say that the arithmetic there was harder than the actual calculus work, personally. Okay, that's it for this section. Thank you for watching.